This is part 2 of timing in digital systems. In part 1, we looked at propagation delay, contamination delay, setup time, and hold time. And we also realized we just have to look at the pipeline segment flip-flop to combinational logic to flip-flop again. A larger design decomposes into many of such segments, and provided each segment works, the whole design will work from a timing perspective. In order to write formulae later on, I am going to give names to each of the delays associated with our components. Flip-flop 1 has got a propagation delay, a contamination delay, a setup time, and a hold time. Our combinational logic has got a propagation delay and a contamination delay. And our second flip-flop, FF3 here, has got a propagation delay, a contamination delay, a setup time, and a hold time. The other thing we have remember is a clock, and the clock period is going to be called P, the time between two consecutive rising edges. For this series, I'm going to assume that there is no clock skew. That means that our two flip-flops receive the rising edge at exactly the same time. Now in practice this won't be true. The insides of the FPGA go to great lengths to try to make this approximately true, but small variations in wire length etc. can result in the clock arriving at one flip-flop slightly before or slightly after at the other flip-flop. That's why it's important that you understand the intuition behind what we're discussing today so that you can extend what we talk about to handle the case when there are clock delays. So don't memorize formulae, instead understand the concepts, because then you can extend it very easily to more complicated situations. Let's remember what happens at the rising edge of the clock. Assume the rising edge occurs at time t equals to 0. That means that flip-flop 1 is going to take a photograph of its input at t equals to 0. Due to its contamination delay though, its output is not going to change until t equals C1, the contamination delay. After a further period of time, the output of flip-flop 1 is going to be correct. That will occur, guaranteed to have occurred, by the time t equals P1, the propagation delay of the first flip-flop. Combinational logic 2 is continuously processing its input. Its input first starts to change at around t equals to C1, and so its output is going to first start to change at C1 plus C2. So t equals to 0 was when there was the rising edge of the clock. This will not change until t equals to C1, and the output of this guy will not change until C2 after its input has started to change, and its input starts to change at C1. Therefore, we know that the output here will start to change at t equals to C1 plus C2. Now, to be pedantic, remember these are promises. So what I should be saying is that we are guaranteed that the output here will not change before this time. Now, it might start to change after this time, that's okay, we don't know. What we do know though is that it will not change before this time has occurred. This is important because remember, a flip-flop has to photograph a constant input to avoid metastability, so we need some guarantees on when the input to flip-flop 3 is not going to change. Now, the other thing we need to know is when the correct answer is going to arrive here, because what we want is flip-flop 3 to photograph the correct answer. So how long after the rising edge of the clock do we have to wait until we have the right answer here? Well, rising edge of the clock takes time for the photograph to propagate through here. At time t equals to P1, the correct output is guaranteed to be here. CL2 can't possibly produce the correct output until it's got the correct input, so CL2 can't start to do its job until t equals P1. At t equals to P1, CL2 has got the correct input here. It can start processing it. Of course, it processes it continuously, but when the input is correct at t equals to P1, that's when we start our clock, because we know it's going to take CL2 P2 units of time to process its input. Therefore, the output here is going to be correct at time t equals P1 plus P2. P1 is when the combinational logic gets the correct input, and P2 is how long it takes the combinational logic to correctly process the input. When does flip-flop 3 take its photograph? Well, in the past we've been saying it takes a photograph precisely at the rising edge, but now we know that we should really think of the photograph being taken at time between the rising edge minus the setup time and the rising edge plus the hold time. So this flip-flop, we have multiple rising edges, remember, but for what we're doing, we just have to consider 2 consecutive ones, but nevertheless, I'll draw 3, whichever you prefer. We know that there's a rising edge at time t equals to 0, because we can just shift, we can arbitrarily decide when to call time t equals to 0 by shifting time. So it's just convenient to make the rising edge line up with time t equals to 0. But once we've done that, once we've fixed one point in time, because we know the clock frequency has got a period of p, we know that this rising edge occurs at time t equals to minus p units of time, and this rising edge occurs at time t equals p units of time. Now each of these flip-flops is going to take a photograph of its input between the setup time before the rising edge and the hold time after the rising edge. So it's within this period that the inputs to these flip-flops must not be changing. Now, because this flip-flop here is going to be at the other end of some other segment here, I don't actually have to worry about this guy here. I just consider the second flip-flop in all my segments, and in this way all flip-flops are going to be covered. Well, you might ask about the very first flip-flop. That's connected to the outside world. And we know that because it's connected to the outside world, we need to use a double flip-flop synchronizer or some other scheme. And if we use a double flip-flop synchronizer, we know there is a small chance of metastability because it's unavoidable. So interfacing to the outside world, we can't do anything about except reduce the chance of metastability. Everything else we can control, and we just have to look at the second flip-flop in each segment, because every flip-flop gets its turn at being the so-called second flip-flop in a segment. So in this way we do cover all flip-flops. This is the key diagram that I've made up. I haven't seen it in books, but it is an easy diagram, and I think it explains everything quite nicely. It might take some time to understand all the detail though, although conceptually it's very straightforward. So let's start. These blue blocks, they represent when the output of flip-flop 1 might be changing. In particular, what we actually care about, well, we care about when it changes, because that then influences when other things change, but we also care about when it doesn't change, or precisely, we care about when the input to a flip-flop doesn't change, because we need the input to a flip-flop to not be changing in order to avoid metastability. So of interest is both when things change, but also when they don't change. That's all I'm trying to say. Anyway, flip-flop 1, we know that at time t equals to minus p, p is the clock period, remember, and we assume there's a rising edge at t equals to 0, therefore there's also a rising edge at t equals to minus p. So at t equals to minus p, there's a rising edge. We know by the definition of contamination delay that the output of flip-flop 1 will not change before the contamination period has expired. So if you like, we know that this time here, this edge of the block is going to be minus p plus c1, the contamination delay of flip-flop 1. We have to wait until the propagation delay is up before we know that the output of flip-flop 1 is correct and will have stopped changing. So this edge of the block is going to be minus P plus P1, the propagation delay of the first flip-flop. So between these two periods of time, the output of flip-flop 1 might be changing. All we know for sure is before the start of this block, the output is constant, and after the output of this block, the output is constant and is the correct value. We don't actually know what's happening in here. We do know something has to happen in here. If the flip-flop is going to change its output, it has to occur sometime in this period, but it might oscillate or do other things. We don't know, we don't care. Exactly the same thing happens at every rising edge of the clock. So therefore, this one here is going to be at time C1, and this edge here is going to be at time P1. This edge here is going to be at P plus C1, and this edge here is going to be at P plus P1. Straightforward enough, hopefully. Now we come to our combinational logic, and the same thing occurs. We know that the input to our combinational logic is the output of our first flip-flop. Therefore, the input to the combinational logic is going to be changing between this period here and this period here. The FF1 output is the input to combinational logic. So the input to combinational logic will be changing between here and here. As soon as the input to the combinational logic starts to change, we wait for C2, the contamination delay of this guy, and then we know that the output might start changing. So we can add that to our diagram here. We know that the input starts to change at minus P plus C1, so the output is going to start possibly going to start changing at minus P plus C1 when the input starts to change, plus C2, the contamination delay of Cl2. When is the output going to be correct? Well, for the output to be correct, first we have to have the input being correct. When is the input to Cl2 correct? That's this point in time here, when the output of FF1 is correct. So the input to Cl2 is correct at time minus P plus P1. Minus P is when the rising edge occurred. P1 is the propagation delay of flip-flop 1. Its output is going to be correct at this time. The input to Cl2 is therefore correct at this time, and we have to wait for its propagation delay to have elapsed before its output is going to be correct. So we now know that the output of Cl2 might be changing any time between these two times. We are guaranteed that its output will not be changing outside of these times. That's the crucial thing. And we are also guaranteed that its output is going to be correct at this edge of this green block here. Those are the only two things we care about: when its output is constant and when its output is correct. By repeating the argument, we know that for the next green block here, its input can start to change at the rising edge, 0, plus the contamination delay of flip-flop 1. That's when this guy's input is going to start changing, so its output is going to start changing at C1 plus C2. And its output is going to be correct when, firstly, its input has to be correct, and then we have to wait for its propagation delay to expire before its output is correct. Therefore, this part of the block is just P1 plus P2. The third block over here, exactly the same thing. Everything repeats with a cycle of P. So I just add P to everything. P plus C1 plus C2, P plus P1 plus P2. Gives me the two edges of this green block here. Now notice in this diagram, the purple blocks represent something different. The blue blocks and the green blocks represent when the output changes of FF1 and Cl2. the purple block is not the output of flip-flop 3, rather it's when this second flip-flop is going to be taking its photograph. When does a flip-flop take a photograph? Well, it takes a photograph approximately at its rising edge, but in fact it starts taking the photograph at the rising edge minus the setup time, and it finishes taking the photograph at the rising edge plus the hold time. For the second purple block, it starts taking a photograph at the rising edge minus the setup time, and it finishes at the rising edge plus the hold time. Same for the third block. Starts its photograph at the rising edge minus the setup time and finishes taking a photograph at the rising edge plus the hold time. What we want for our pipeline segment to work is that the third flip-flop takes a photograph of the correct answer. Now remember, it takes time, so at this rising edge we photographed what the previous worker has done. We take a photograph of what the current worker, CL2, has to do. We take a photograph of its input at around the rising edge, but it takes time before that actually reaches our little worker here. Our worker receives the correct thing to do at time minus p plus p1. And our worker, working very hard, produces the right answer at time minus p plus p1 plus p2. P2 is how long this worker needs to do his or her job once the correct input has arrived. Only once CL2 has finished processing the data do we want our second flip-flop to take a photograph. If this flip-flop takes a photograph any earlier, it's not going to have photographed the correct output here. So, one requirement then, notice this faint green line here. I have to have that on the next rising edge, so this is the rising edge that brought in the hamburger to this worker to process. The next rising edge is when that hamburger is going to move along again. So hamburger comes in, hamburger goes out. We have to make sure that when the hamburger goes out, when the conveyor belt moves along, when this flip-flop takes a photograph, that has to occur after this worker has put the tomato on the hamburger. And that occurs at the green line here. So therefore this purple block has to be after this green line here. That means this worker's finished doing his or her job by the time the conveyor belt moves on. Now the other requirement we have is that this flip-flop takes a photograph of a stable input. Its input must not be changing. Now its input, so once CL2 has finished adding the tomato to the hamburger, that's it. That hamburger is not going anywhere. No one's going to eat it or touch it or anything. It just sits there. So it can sit here for 5 days. Hopefully I don't have to eat it, but it could sit here for 5 days before the next rising edge comes along, and that's not a problem. We just have to have the photograph starting to be taken after the hamburger has finished being processed by this worker here. But remember that once that hamburger starts to be photographed, it has to remain not doing anything for the duration of the photograph. Now, provided there's no clock skew and provided the two flip-flops are matched, you're guaranteed that the output is going to stay constant while the second flip-flop is taking a photograph. However, if there is clock skew or if these flip-flops are not matched up, it is conceivable that the input to the second flip-flop can start to change while it's still taking a photograph. So what that means has happened when things go wrong is that at this rising edge here, the first flip-flop is super fast at taking a photograph and starts to change its output very early on. The worker, the same worker that put the tomato onto our hamburger, this worker might also be super fast at starting to do something. And so if there's a rising edge here, the output to the first flip-flop starts to change soon after. And if this worker starts to do something to that hamburger soon after, it might be that it started to process the next hamburger before this flip-flop has finished taking a photograph of the previous finished hamburger. That's the second thing we need to avoid. So we have these two timing constraints, and there are only two timing constraints. We simply have to have that the second flip-flop starts to take its photograph after the combinational logic has produced the right answer. And we have to make sure that the same combinational logic, the same worker, doesn't start on the next hamburger until after our second flip-flop has finished taking a photograph of the finished product. Now notice on this diagram we've actually labelled all the times here. So to say that we want this to occur before this is simply saying we want minus p plus p1 plus p2 to be less than minus s3. How easy is that? And similarly over here, because we want this to occur before this, all we're saying is we want h3 to be less than c1 plus c2. And that's it. If you can intuitively draw this diagram, you just go bit by bit, slow and steady wins the race, then you can just read off the answer and you can be 500% confident that you've gotten the right answer. This is so much better than trying to memorize formulae and then finding an exam question where things are a little bit different and becoming stuck because it doesn't fit entirely into the thing you memorized. The concept here is very straightforward. We just label everything according to the definitions of propagation and contamination delay. That's straightforward. And we figure out when our flip-flop takes a photograph. That's straightforward. And we make sure that the photograph occurs between these two events here. And that's it. Conceptually, very straightforward. Before we get to the mathematics, which is nothing more than just writing down what's on the diagram we drew before, it's worth asking the question, well, if our timing does not work, how do we fix it? Well, there are two things we have to control, remember. The first one is we have to make sure that this flip-flop takes a photograph after the worker has finished with the product. The red lines here, so this diagram is periodic. You'll notice everything is periodic here. And the period is given precisely by the clock period P. So if I were to make the clock period longer, if I were to increase P, then this line here goes to the left and this line here goes to the right. And you can imagine, and remember, so with this line here, this blue block, this green block and this purple block are all aligned with this red line here. So when P increases, all three of these guys here go to the left. And all three of these guys here go to the right. And these three, because they're centered at t equals to 0, they don't go anywhere. So in particular, as P increases, these three things go to the left. These three things stay the same. In other words, I get a bigger gap between this green guy here and this purple guy here. So I can always make sure that this edge occurs before this edge simply by choosing P large enough. In practical terms, I'm saying I just have to work out how long it takes this guy to make the hamburger and then don't move the conveyor belt until after he's finished. I just increase P until he's had time to do his job. So I can always make sure that there's a gap here by increasing P. And by the way, P is 1 on the clock frequency. And so we can see now what Quartus is telling us when it gives us F max. F max is when the clock period is such that this point here lines up with this point here. If we try to drive our circuit any faster, we've got overlap and it might not work. Now, for later in the course, I should just add, if I can't make the clock frequency slower for other reasons, for other constraints in my design, then I have to simplify my combinational logic. I might have to say, well, this guy is trying to do too much with the hamburger. Rather than making him add the lettuce and the tomato, I'll just get him to add the lettuce and then let the next guy add the tomato. And then I can move the conveyor belt a bit faster. That's known as pipelining. So we can make the clock period slower. We can make the combinational logic simpler, but having more of it in different stages. However, what is harder to fix is when we have an overlap in this direction here. The only way to fix that is to, well, I guess we could mess with the clock timing, introduce an offset to the rising edge of the clock here, but we don't really want to do that, because what we really want is for all our flip-flops to be clocked at exactly the same time, and the FPGA architecture tries to achieve that. It's not perfect, but it tries to achieve that. I guess in exceptional cases you could play around with the specific placement of individual flip-flops to try to get a rising edge occurring a bit earlier for this guy here to leave more margin for error here. But otherwise, so fixing this problem here has to do with playing around with the actual components. If there's no clock skew and if these flip-flops are matched up, there shouldn't be a problem here. So it's more of a theoretical issue in this course. So in terms of meeting design requirements, we take the diagram from before and we just write down the two inequalities that I told you before. So maybe it looks a bit complicated here, but this just comes from that diagram and the constraint that the purple block sits between the two green blocks with no overlap there. And that's it. Now again, I warn you, don't memorize these guys here. Instead, be able to recreate that diagram and then read off the answer. That's the much safer way of doing things. I've skipped a few slides because they just cover things that we've already discussed, but I should emphasize that making sure that this purple block lies to the left of this green block, changing the clock frequency isn't going to fix that. As you were saying before, that's more of a design problem. It means that there's clock skew present or these flip-flops aren't matched up. Changing the clock frequency is not going to change the distance from this purple block to this next green block here. Satisfying the time constraints is known as meeting timing closure. That's the term that Quartus is going to use. And it's Quartus's job to check whether or not we have met timing closure. Why is it Quartus's job? Well, only Quartus knows the precise timing inside the FPGA. Based on based on what flip-flops it's allocated to our design, what lookup tables it's allocated, etc., it can work out the propagation delays and in the wires, and also the contamination and propagation delays of the lookup tables and the flip-flops, and it knows the setup times and the hold times. Only Quartus knows all of that. But Quartus doesn't know the clock frequency. Remember, the clock goes into the pin of our FPGA, and how does Quartus know what frequency it is? We have to tell it, and it's in one of the configuration files, the .sdc file, and there's a specific command that you learn in the labs that you put in that file that tells Quartus which pin contains the clock and what its clock frequency is. And Quartus then uses that and does exactly the same calculations that we have done to work out whether the design will work or not. It is worth emphasizing that our timing approach works for finite state machines. You might say, well, with a finite state machine, I just have a single bank of flip-flops. I don't have flip-flop combinational logic flip-flop. But remember, we can treat this flip-flop as both the first and the second flip-flop. The input comes into our first flip-flop, it then goes through some combinational logic and then back into the next flip-flop. The fact that it's the same flip-flop is irrelevant from the point of view of our analysis. Our analysis is exactly the same as before. We may as well treat it as two separate flip-flops. So a typical question might be, we're told that our transition logic has got a propagation delay of 5 nanoseconds and a contamination delay of 1 nanosecond. And we're told the flip-flops have got a propagation delay of 2 nanoseconds, a contamination delay of 1 nanosecond, a setup time of 1 nanosecond, and a hold time of nanosecond. And we're told that for the output logic here, there's a propagation delay of 8 nanoseconds and a contamination delay of 2 nanoseconds. And we can ask the question, will this design work? One thing to point out, because we haven't been told what this output connects to, it's going to go into either more combinational logic or into a flip-flop. So for example, if this finite state machine if the output gets fed into another finite state machine, so then that means that the output here is actually going to go into another finite state machine. It's going to go through some combinational logic first and then into another flip-flop. So to work out if that works, we have to combine this combinational logic with this combinational logic to work in our figure before. So we've got flip-flop, combinational logic, more combinational logic from the second finite state machine, and then hitting the flip-flops. We just combine these two. How do we combine two combinational logic? Well, intuitively, the propagation delay of two combinational logic circuits in series is just the sum of the propagation delays. First I have to wait for this guy to get the right answer, then I have to wait for this girl to get the right answer, and then we're in business. And similarly, the contamination delays are going to add. This output is not going to start changing until the contamination delay period's expired. That's when the next combinational logic's input's going to start changing, so we add its combinational delay to that to get the output. So we can just combine these two together, and then we're back to our very standard case of all we do is analyze flip-flop, combinational logic, flip-flop. So for this question here, because we don't know what's out here, all we have to worry about is flip-flop, combinational logic, flip-flop, and ask, does it work? That means, is the purple block going to be finished? Is the second flip-flop going to have finished taking a photograph before the input starts to change again? That's will it work, part 2, so to speak. And will it work, part 1 is the clock period sufficiently slow so that this combinational logic circuit has got enough time to get the right answer before the next rising edge? In other words, does the end of the last green block occur before the start of the purple block? Does the combinational logic give the right answer before our flip-flop starts photographing the input? We need to answer these two questions here, and answering the question about how long this combinational logic needs to do its job will tell us what Fmax is. That's it. While the answer's given here, it's just a case of going back to the diagram, figuring out what's going on, and then making sure that the purple block sits between the two green blocks. That's all it is. And then once you've done that, you can ask, well, when does the green block just touch the purple block? So remember, when we adjust the clock period, we're making the first 3 blocks get closer to the next 3 blocks. So what's the smallest p that will get the green block to just touch the purple block? Well, that's p min, I've called here. And then f max is just 1 on this smallest clock period here. That gives us the f max of our design. For those of you that have access to my lecture notes, there are a few more details in there, but I've covered all the important concepts. And therefore this concludes our 2-part video series on timing in digital systems.